All right, there's one other thing we need to talk about. In 5.2, we found the mean of a probability distribution. So we should be able to find the mean of a binomial probability distribution and also its standard deviation and its variation. We just need to be able to interpret these values and use them to say whether a certain value is unusual or not unusual. The formulas that you need for binomial distribution parameters are the mean, the symbol for the mean of a probability distribution is mu, and the mean is just the number of trials times the probability of success. Think about it this way. In 5.2, we said expected value means the same thing as mean. If I say I have a population of, or a sample of 100 people and 15% of them have blue eyes, how many would you expect to have blue eyes? You would just say 15% of 100 is 15. So the expected value is 15. That means the mean is 15. The variance, symbol for variance is sigma squared. The variance is n times p times q. Remember, q is the probability of failure. And then the standard deviation is just the square root of the variance, the square root of n times p times q. Just as we have been doing, if we want to find a range of usual values, you can say the highest usual value is the mean plus 2 standard deviations, and the lowest usual value is the mean minus 2 standard deviations. Anything within that range is considered usual. Anything outside that range would be considered unusual. Mars Inc. claims that 24% of its M&M plain candies are blue. A sample of M&Ms is randomly selected. Find the mean and the standard deviation for the numbers of blue M&Ms in such groups of 100. Well, we're given that the sample size is 100, and Mars says the probability that any individual M&M is blue is 0.24. So if I just said, how many blue M&Ms are you expecting? You could say 24% of 100 is 24. In a group of 100 M&Ms, I'd expect 24 of them to be blue. That's just really the definition of percent. If you had a problem that you could not do that in your head, you would say the mean is n times p, or 100 times 0.24, and get that the mean is 24 blue M&Ms. And remember that that means the same thing as expected value, the number of blue M&Ms I would expect to get in a bag of 100. I'm also supposed to find the standard deviation. Let me do that out here. The standard deviation is the square root of n times p times q. For this problem, that's the square root of n is 100, p is 0.24, and q is the complement of p. If the probability of a blue M&M is 0.24, the probability of a not blue M&M is 0.76. So the square root of 100 times 0.24 times 0.76 is about 4.3. So I'm expecting 24 blue M&Ms with a standard deviation of 4.3. Let's go ahead and get the minimum number of blue M&Ms and the maximum number of blue M&Ms. Remember that the minimum is the mean minus 2 standard deviations, and the max is the mean plus 2 standard deviations. So for this problem, the minimum number of blue M&Ms would be 24 minus 2 4.3s. That's 15.4. And the maximum usual number of blue M&Ms would be 24 plus 2 standard deviations, or 32.6. That means I'm not going to be surprised if my bag of 100 M&Ms has between 15.4 and 32.6 blue M&Ms, but 10 would be surprising, unusual, because it's less than the minimum usual value, and 40 blue M&Ms would be unusual because it's more than the highest expected or highest usual number of blue M&Ms. The question in the B part is, would 27 be unusual? Well, 27 is between this minimum usual and maximum usual. So I'm going to say no, 27 blue M&Ms would not be unusual. If you ask me for a number that would be unusual, I would just say any number less than 15.4 or any number greater than 32.6. Does it seem, if I did get this bag of M&Ms, 100 M&Ms, and it had 27 blue, would I think Mars was lying to me, that that claimed rate is wrong? No, because 27 would not be an unusual number of blue M&Ms, even if the rate of 24% was correct. We have one more problem, and it illustrates how sometimes statistics are used to scare people. I remember when there was a concern about whether or not cell phones use cause brain cancer. So a group in Denmark studied 420,095 cell phone users, and it was found that 135 of them developed cancer of the brain or nervous system. At first glance, that's very scary. I wonder if using the cell phones caused these 135 to develop brain or nervous system cancer. Well, medical researchers, medical researchers, I can't say medical researchers. Medical researchers tell us that the probability of developing that particular type of cancer, whether you use cell phones or not, is 0.00034. So even if you had never held a cell phone to your ear, there's still a chance that you would develop that type of cancer. Let's see how many people we should have expected to get that type of cancer out of that study group, even if the cell phones were having no effect on the cancer. Well, expected value again means mean, and the mean is the trial size or sample size times the probability of success. Since we're studying the number of people who develop cancer, we're saying developing cancer actually in this situation is success, or this type of cancer, and the probability of success is 0.00034. So the number of people that I would have expected out of that 420,000, the number that I would have expected to develop that type of cancer, rounded to the nearest whole person, is 143. Actually, fewer people developed cancer than we would have expected to, even if the cell phones didn't have anything to do with the development of that type of cancer. We also want to find the standard deviation. That's the square root of the 420,095 times the 0.00034 times the complement, or 1 minus 0.00034. And I got that to be about 12. Notice if one standard deviation is 12, then two standard deviations would be 24. So I really wouldn't be surprised if between 143 minus 24 or 143 plus 24 people had developed that cancer. I would say the max, or I'm going to call it just the usual range, the mean plus or minus two standard deviations. 143 minus two standard deviations is 119, and 124, no, I'm sorry, 143 plus 24 is 167. Anywhere in that range would not have been considered an unusual number of people to develop this type of cancer. So in the B part, based on our results, is it unusual to find in that sample there were 135 cases of that type of cancer? No, that was within two standard deviations of the mean. And what do these results suggest about publicized concern that cell phones are a health danger because they increase the risk of cancer? I'm just going to say that's bogus. I would have actually expected more than 135 people out of this sample size to develop that type of cancer, even if they had not used cell phones. All right, just to recap what we've talked about in 5.3 and 5.4, you should be able to identify the binomial probability distribution. You should be able to find the probability of X successes, exactly X successes, or at most X successes, or at least X successes in N trials. You should be able to find the mean, the variance, and the standard deviation of a binomial probability distribution, and you should be able to identify usual and unusual outcomes. So that's it for 5.3 and 5.4. That's actually all the material that is covered on test 2. So you're ready to begin the practice test. Let me know if I can help.